Good morning to all of you. So please go through whatever we did in the last class and then we'll continue. Are there any questions, doubts? Okay. So are there any other questions? Product design students are here. So then let me start. So one question was about, we had weak forms, if you recall the weak form of the problem under consideration. So we had this weak form which was actually written as the boundary terms where we had minus, then integration, that was with so y1 to y2 and w into k del t by del x evaluated at x1 x2 dy. This was one, and the other boundary term was minus x1 to x2 wk del t by del y evaluated at y1 and y2 dx. So these were the boundary terms, and of course the remaining ones. So this is what we had, right? These are the boundary terms, and these boundary terms we said that we can write as essentially integration over the closed contour and then w into qn ds. That is what we said. Now let us look at for the problem. The question asked was how we can get from this again back this. So the domain we had was this, and the I had said of course that no xy is somewhere, let us say here. So then this edge is what you have as x is equal to x1, this edge is x equal to x2, and this is y equal to y1, and this is y equal to y2. So now let us start with this edge. So this integral is in counterclockwise direction, going like this. So from this how do we get, is that your question, right? So now from if you want to expand again this w, q and ds, so we again go along this edge from this point to this point. Now for this edge, if you look at obviously your this particular edge is y equal to y1, and ds is going to be simply dx, because now the s is, let us say this point is s equal to 0, and then you are going this side. So s and x, they are same, and so you can say that s equal to 0 is corresponds to x equal to x1, and s is equal to whatever is the length of this edge corresponds to x equal to x2. So for that we can write this integral from x1 to x2, and of course we have this w, and then ds means we are writing as dx. Now what happens to this qn? Qn we had said that this is equal to minus k into del t by del n. That is what we had defined as this qn, right? Now for this edge the outward normal is along minus y direction. So your n is actually minus y. So what do we get? This n is minus y. So you will get this as here k into del t by del y, and obviously this we are evaluating at y equal to y1. So this whole thing is evaluated at y equal to y1. So do we get the this lower boundary from this lower boundary term here? From this one is upper boundary term, that is y equal to y2, y equal to y1. For the lower boundary you will have minus minus plus, so this is what is here. So and then let us look at along this boundary what do we get. So interpretation of this. Now here if you look at your s is actually along y, so you can write that integral as ds is equal to dy. ds has dy, and then whatever is the value of s corresponds to y equal to y1 here and y equal to y2 here. So the integration limits I can put from y1 to y2, and of course w, and then let us see what happens to this qn. So outward normal here is along the x direction. So n is x, so qn is going to be, for this boundary, qn would be equal to minus k into del t by actually del x, because no outward normal is along plus x direction, so this sign remains there. So then for this boundary you will have a minus sign here and k into del t by del x, and this is evaluated at x is equal to x2. So which term we get out of this? We get the upper boundary term here. It is as it is, no minus sign, integration from y1 to y2 w k del t by del x, evaluated whole thing is evaluated at x equal to x2 into dy. So that's the second term. Then now let us look at the when we are going along this boundary now. So for that boundary, actually what you would be doing is you would be going from here to here. So in the closed contour integral evaluation. So first let me write as it is. So now your ds is one is that your ds is going to be actually minus dy, because y is increasing in this direction and your ds is going in this direction. So you will have, and then the integration limit is from here to here. So let me put that as x2, and then this as x1, and ds is minus dy, ds is minus dx. So I will have minus dx w here, and then what would be qn there? Qn for this particular edge, qn is minus k into del t by outward normal is along plus y direction. So it remains as it is, minus k into del t by del y, because n is equal to y. So you get that minus here, minus let me put here k into del t by del y. So of course this minus and this minus would actually become plus. This is evaluated at, this whole thing is evaluated at y equal to y2. Right. So this minus will become plus, but then the limits are x2 to x1. So you can put another minus sign and make this integral from x1 to x2. You can reverse those limits. So then you see what you get out of this term. The upper boundary term here will be with a minus sign wk del t by del y dx evaluated at y equal to y2. So this is what you have basically. This minus minus plus, again one minus, by interchanging the upper and lower limits, so that you are going along positive x direction. So same way when you come to now this edge, for this edge again see your ds is going to be equal to minus dx, because as per the contour integral you would be moving in this direction, whereas x is positive in this direction. So you will have again say the integration here, and this is going to be minus ds is minus dy. You are moving along negative y direction as per the contour integral, and then the integration limit is again you are going from here to here. So that is from y2 to y1 w, and then qn is, if you look at the outward normal, is along minus x direction. So for this case qn is minus k del t by del minus x. You follow that, no? So this is what, because your outward normal is along negative x direction, so this would become k into del t by del x. So you will have k into del t by del x. This is evaluated at x is equal to x1. So and now if you see this term x equal to x1 here, so it's a lower boundary term, that is putting minus minus would become plus. So we should have a plus sign here. So already you have a 1 minus sign here, and then when you go interchange these limits y1 to y2, you will get 1 minus, so minus minus will become plus. So you would see that all those 4 terms are actually incorporated in this. So you can interpret like that's what we had done in the last class. So are there any other questions, or if there is any doubt in this itself? So that is how you interpret those boundary terms. So then let me continue. So last class what we did was finally we had reached to the element level governing equations. And what we had said, no, I am not going to repeat all of those what we did, all the steps, but what we had, no, we consider a triangular element, and say the origin of the coordinate system is here, this node 1, and this is node 2, this is node 3, and so we said that for within this element the governing equation is Ke into dE is equal to, we had F external for the element and plus no, F internal, and by definition, no, the derivation we had got Ke as the integration over the entire area now of this triangular element, not of the domain, K into B transpose into B dx dy. So this was the expression for no, coefficient matrix, and then we had F external, which was due to internal heat generation. So this was again the integration over the entire domain, and we had this as H transpose into Qg dx dy. H and all we had defined, and then F internal for the element was, I think we had a minus sign right in this, so this was a contour integral, and we had H transpose Qn ds. So this is what we had done in the last class. Now let us look at little more on this. So if we look at the stiffness matrix, we had already defined what is B. So if you further look at Ke for the purpose of using this ultimately in the problem solving. So if you look at this integration over area K, and your B, if you look at we had defined this B. So if you look at your notes, you will have B, which is 1 upon 2a, and then we had here, what was the first term? This was y1 minus y. L1 is 1 xy, 1 x2 y2, 1 x3 y3. So del L1 by del x is actually this, so you strike out y3, so y2 minus, so this was y2 minus y3, right? And then you have this as y3 minus y1, and next term like that, and similarly you have when you take the derivative with respect to x, you get x3 minus x2, and then you get x1 minus x3, and one more term, you can write there. So if you look at, now this B is actually constant. See, because we are assuming linear temperature distribution within the element, so its gradient with respect to x and y is actually constant. So that means when you are doing the integration here, if you look at B transpose B is actually going to be constant. So what I can do is, whatever we have here, there is no B transpose B dx dy, we can actually write this as, and assuming that thermal conductivity is also constant within the element, so you can take this whole thing out. So you can write this as K into B transpose into B, and then the integration over the entire area into dx dy, isn't it? Because for this particular case B is constant independent of x and y, so can be taken out of the integration. And now what would be this integration over the entire domain dx dy will give you the area. So actually this would be simply K into A into B transpose into B, that is what you are going to get as the Ke. So actually you do not require to do any integration here, it simply comes in this form. And of course B so here whatever B is there and its transpose, you put all of that here, and then you can work out the stiffness matrix, the coefficient matrix. So this is your Ke, and of course you will have to evaluate the, depending on the given situation, you will have to do the evaluation of this integral, evaluation of this integral, depending on the problem. So the next what I am going to do, just take a simple example. So first I want you to attempt this. So let us say that we take a simple problem wherein we have, let's say, a rectangular slab with certain boundary conditions. So this is a rectangular slab, and let us say the coordinate origin is here itself, this is x and y. This side, let us say there is a boundary heat flux input. Let us say this is something like 2 watts per meter, and this edge, this entire edge is maintained at a certain temperature. So let us say that no, here T is equal to 100 degrees Celsius, and for these two edges these are insulated. So let us say that Qn is 0 here, Qn is 0 here, and you also need dimensions. So let me say that this is 2 meter by 2 meter, a square slab for the time being. Okay, so let us say now this is also 2 meters. What you want is, you want to find out the temperature distribution within this slab under this condition. Now what we have done is, we have formulated only 3 noded triangular element. So that is what we can use for solving this problem. So you can discretize now into actually a number of triangles, but at the simplest level what we can do is, we can discretize this into 2 triangular elements. So let me say that one, I just take an element from here to here. So this is element, let us say 1, and this is element number 2, and the nodes are, this is one global node number, this is another, this global node number 3, the global node number 4. So this is 1, 2, 3 and 4. These are your global node numbers, the element number 1 and 2. You will have to, and there is no heat generation, so Qg is 0. So for this problem, Qg is equal to 0. Now just try, how will you, so there are 2 elements, you will have to, obviously you know the element level coefficient matrix for both the elements is given by this expression. Of course, since the coordinates are different, so it would be different, but you will have to evaluate. So first you have to evaluate the matrices for the first element, and then the matrices for the second element, assemble them, impose the boundary condition and solve. So for element 1, what will you do? Yes, you need coordinates. See, these are global node numbers 1, 2, 3, 4. What you actually need is, for the first element, if you look at the local coordinates, are rather, you know, in terms of local node numbers. So let me not say the local coordinates, but these are, you can say x1 equal to y1 equal to 0. That is, this is the first node, and we were going in the anti-clockwise sequence. So second is x2 is equal to 2 and y2 equal to 0. Then if you look at, you can take 1 to 4. So actually for local third node is global fourth node. So let me still say x4 is also 2 and y4 is 2. So you are going to choose, actually in terms of local numbering scheme, this has x3 and this has y3. In your expressions. So these are the coordinates. You need the area. So area of this is going to be half. In this case it is straightforward. You can always, of course, go through the determinant, but in this case the base is 2, so have 2 into 2, which is basically 2 square meter is the area. So this you know. Then what you need is your B. B is equal to 1 upon 2a, which is basically 4. And then here what you have is, so just now you saw this is y2 minus y3. So y2 minus y3 would be minus 2. Please correct me if I am going wrong. Y2 minus, I have just written with respect to 1, 2 and 4 are actually the, for this global node 1 is the first node of the element, global node 2 is the second node, global node 4 is the third node of the element. So I have just written here the coordinates x4, y4. That's also I have written in bracket. This is actually in local node numbering of element 3. This is x3, y3. Okay. So now as per the, you need to evaluate this y2 minus y3. So as you see, y2 minus y3 is minus 2. Then you have y3 minus y1. So y3 minus y1 is plus 2. And then you have got next is y1 minus y2, and y1 minus y2 is actually 0. And then what you have is x3 minus x2. So x3 minus x2 which is 0, and then you have this x1 minus x3, x1 minus x3 which is minus 2, and then you have x2 minus x1, so x2 minus x1 is plus 2. So this is your B matrix for the first element, is that right? This is a matrix, you can actually take this 2 out, so you can in fact write this as 1 by 2 minus 1 1 0 0 minus 1 and 1. So this is your B matrix. So is it okay? So we just now, if we want to use for 2D problem, how do we go about solving problems? Of course you can always write a computer program, say in MATLAB, and you can do these things essentially through the program. But to understand what goes on is this is what you do. So k is equal to, as we have looked at the formula here, k is let some value k, we take it in the form of k itself. So this is 2k, area is A, and then you have B transpose k into B transpose into B. So this is k into A, then B transpose into B. So this 1 by 2 actually will have 4, and then what you are going to have is the transpose of this, which is minus 1 0 1. You can actually do that. So this is minus 1 0, then 1 and minus 1, and then you have 0 and 1. So minus 1 1 0 0 minus 1 into B transpose, which is minus 1 1 0 0 minus 1 1. So if you do this, you get k by 2, finally your element label for the first element, the coefficient matrix. And so if you do the multiplication, this into this, so it gives you plus 1, and for the second one again it gives you a minus 1, and then this will give you 0. Is that right? Please do yourself and tell me what do you get. So 1 into minus 1, you get a minus 1 here again, and this into this will be 1 plus 1, which is 2, and for the third one it would be minus 1, and the last one is this is 0 obviously, and then this is 0 minus 1, and then the last one is 1, right? So this is the coefficient matrix for the first element. In the first element, you also have this distributed flux which is there, and on this edge 2 4. So we will have to Qg is 0, so there is no contribution, and of course this is the interface between the two elements. So there also you can have some heat transfer either from this element to this element, or from that element to this side. You can have heat flux there, but what will happen is you need not evaluate the internal load vector along this edge, because whatever you get from the first element and when you assemble with the second element, they will actually cancel out. So you need not worry about that. So I am not going to evaluate that part, because even we do not know what is the flux distribution Qn along this edge, but this is externally given. So actually ultimately this edge flux can be accounted through the cyclic integral. So we will still call that as let us say F internal. So although it is actually external heat source there. So F internal for the first element, as per whatever derivation we did, this is cyclic integral. So H transpose into Qn ds, this is what we are going to do, but this we are just going to evaluate only across this boundary. So that boundary is again ds is actually equal to dy, and the limits are from 0 to 2. So I can say that this is from 0 to 2, and H of course we will have to look at H transpose. Q is given as, and now this heat flux is entering into the boundary, so it is actually minus 2. So you will have this, of course we had used a minus sign here. So this minus, and then this is dy. Is that right? This cyclic integral only I am considering over this edge. For this is anyway the Qn is 0, so you do not have to worry about that. There can be an unknown heat flux here, but we are not evaluating that part. That I will explain you. When you are assembling, it will actually go to 0. So now this is integral 0 to 2, and your H transpose, which is going to be basically L1, L2, L3, and let me write that 2 outside dy. Is that right? And this is to be evaluated at x is equal to 2. X is equal to 2. because we are going along that boundary. No, the boundary here is x equal to 2. So now can you evaluate this? So 2 integral 0 to 2. Now expressions for L1, L2, L3 you need. Let me put in the vector form dy at x equal to 2. So what is your L1? L1 is, if you recall, 1 upon 2a, so which is 4, and then this determinant 1 xy, and then 1 x2 y2, 1 x3 y3. Can you please evaluate this? And x is already 2, so it's only function of y finally. Similarly, you need L2 and L3. So this will turn out to be, yes. So let me evaluate this. So 1 by 4, and then the first term will give you, finally of course you'll have to put the coordinate values. So this is x2 y3 minus x3 y2, that's the first term, and then you will have a minus x into what you have is y3 minus y2, and plus y into, and then you have x3 minus x2. This is your L1. Now in this you put your coordinates. So 1 by 4, what are the values of x2 and y3? x2 is 2 and y3 is also 2. So this is 4, and x3 is 2 and y2 is 0, so that becomes 0, and then minus x, and x itself is actually 2, so we have this as actually what should be the value of L1? It should turn out to be 0, so we will see that this is actually, even if we put x as it is, so minus x into, this is y3 minus y2. What is the value of y3 and y2? So this is 2 minus 0, so this is actually 2, right, and plus y times x3 is 2 and x2 is also 2, so this is actually 0. So finally you get this as 1 by 4 minus 2x, and when you put x is equal to 2, because no, this is to be evaluated at x equal to 2, so this will be 0 at x equal to 2. So when you evaluate this, L1 is actually 0, right? Because no, you have to evaluate this integral, and that is why we need know these L1, L2, L3. So that's why I am doing this. So same way, if you look at L2 and L3 of course would be non-zero. So this is 1 upon 2a, and again 1 xy, and L2 means then this is first 1 x3 y3, 1 x1 y1. Is this right? As per no, the derivations we did. So please just work out similar way. What is this L2 at x is equal to 2? Finally x you are going to put as 2. So this is also then similar way, 1 by 4, and then no, the this is x3 y1. So we have already evaluated x3 y1 minus x1 y, no, these are different ones, yeah, okay. So this is x3 y1 minus y3 x1, and minus x into, then you have y1 minus y3, and then you have plus y, which is x1 minus x3. So now if you evaluate this, 1 by 4, x3 is equal to 2, y1 is equal to 0, so this is 0, and then x1 is also 0, so the first term is 0, is that right? So this is 0 minus x, then y1 is 0, y3 is 2, so this is 2, and this is x1 minus, what we have is the last term, x1 minus what did I write? x1 minus x3, no? So y means, yeah, x1 minus x3. So what is x1 minus x3? Again 2. So this is plus 2y. So what you will have is, this is going to be finally minus x by 2 plus y by 2. So this is how no, your shape function L2 along that edge, and when you evaluate this at x is equal to 2, you get minus 1 plus y by 2. So here you will get minus 1 plus y by 2. Okay? Are you with me or no? This is simple calculation actually. you can also do. So what is similarly L3? Can you just do the similar calculation and tell me? So this is what I have done here. Similarly, what would be value of L3 at x is equal to 2? Yes? So here second term is y1 minus y3, yes, is minus, actually will become plus, so this is plus here. Yeah, correct, thanks for correcting that. So this is going to be plus. So it is always better to write a computer program and do these calculations, okay, but at least one problem you should do so that you understand what goes on in that. So yes, what is the value of L3 at x equal to 2? 1 minus y by 2. I think this is correct because along that edge L2 plus L3 should be equal, because anywhere you will see the one property of these shape functions is that throughout the triangle L1 plus L2 plus L3 must be equal to unity, sum of all the shape functions, because it's the area ratios. So when you sum the three areas you get the area of the total triangle. So you will see also along that edge we are going from here to here. Along this also L1 plus L2 plus L3 would be actually equal to unity, and that is what you see, L1 is 0 plus L2 plus L3. There should be no, there has to be some by 2, or I am missing something? So this, because finally the shape functions should sum up to L1 plus L2 plus L3 must be equal to unity. So far I missed something.
L2 is 1 minus y by 2.
1 minus
y by 2. And L3 is y by 2.
this L3 is plus y by 2. But still I get 1 plus 1, which is
L2 is 1 minus y by 2. L2 is 1 minus y by 2 in the second term.
I think somebody has to check it carefully. 1 minus y by 2, and then L3 is only plus y by 2. Yeah, okay, so that is what I thought. So if then it's fine. Then of course you have L1 plus L2 plus L3 equal to unity. That is what should happen. So where did I make mistake here? This is minus 2y. Okay. But then this term should be 0, no? No, so let me just say L2 is 1xy, then there is, because I am writing for 2, so it will be P31, so that's right, 1xy, 1x3y3, 1x1y1, that is fine. A is 2, so 1 by 4, and the first one is x3y1 minus y3x1, then minus x into this goes, so you have y1 minus y3, this is right, plus y, and then you have x1 minus x3. So what I have written there is correct, 1 by 4, then x3 is 2, but y1 is 0, so it goes to 0, and then x1 is 0, so therefore the first term is 0. Then you have here x, so right now minus there, but y1 minus y3 is minus 2, so minus minus plus 2x you get, and then x1 minus x3 is minus 2, so this should be minus 2, right? This should be minus 2. So finally you get this as an x is equal to 2, so for that edge you get 1 by 4, so basically 1 plus minus, yeah, okay. So this is correct, so 1 minus y by 2, and then this is also okay. Okay, so that's what we got. Now this vector evaluated at x equal to 2, and now you can do the integration straightforward. So integration 0 to, so let me do now the integration. So the first is obviously remains 0, and what would be the integral of second? That would be y minus y square by 4, and then put the limit. So what do you get? y minus y square by 4 when you put the limits 0 to 2. So this is 2 minus 4 by 4, so actually 1, right? And for this it is y square by 4 when you put the limit, so that's also 1. So finally get this vector as 0 2 2, right? So this is the contribution of this distributed heat flux to the load vector of this particular element. Since this is acting along an edge, so we have taken it through the contour integral. Okay, then as far as the second element is concerned, although there is going to be some heat flux here, but that's an unknown quantity. Similarly, there is heat flux here, of course, 0, and as I said, there is going to be some heat flux here, and the heat flux from this side and this phi contributions to that these two nodes would actually cancel out, so we are not evaluating that. So for the second element, you only have to evaluate. Now say we take element number 2, you have to just evaluate the K. For that, the coefficient matrix Ke, which is we had said that is K into A into B transpose into B, and area for this element is also same. It is identical triangle. So this is 2K, and then what would be now you have to, so before I can write this, you need your B. So for this element, what would be B? 1 upon 2, that is 4. Yes, what would be B for the second element? Now the local node numbering, say the local node numbers for this second element are, this is 1, so you can again go in the anti-clockwise second, so sequence. So let us say locally this is the node number 1, this is node number 2, and this is locally node number 3. So x1 y1 are 0 for this element. So you would see that x1 equal to y1 equal to 0, and then your x2 y2 are 2 2, and then so x2 equal to y2 equal to 2, and x3 is 0, and y3 is equal to 2. Okay, so these are the coordinates. Here 1 2 3 are local node numbers, and that is the numbering scheme I have used. That first node of the second element is global node 1, and second node of the element 2 is the global node 4, and third node of the second element is global node 3. This aspect you will have to keep in mind at the time of assembly. So the nodes I have taken here in the anti-clockwise sequence 1 2 3, so they are global node numbers 1 4 and 3. So now if you these are in terms of local numbers, so that you will have to keep in mind. So what is B? We start with what was that B I wrote somewhere? So y2 minus y3. So we start with y2 minus y3. So y2 minus y3, which is 0, and then you have y3 minus y1. Y3 minus y1 is 2, and then y1 minus y2. So y1 minus y2, which is minus 2. Is that right? Then the second row is, what we have is x3 minus x2. So we start with x3 minus x2, which is minus 2, and then x1 minus x3, x1 minus x3 remains 0, and then is 2. Okay, so this is what you get as your B. So again you can take actually that 2 outside, so you can write 1 by 2, and then again 0 1 minus 1 minus 1 0 and 1. Little bit more involved, so that you need to bear with that. So now this you can write as K, which is we are taking as it is. So this is 2K, and then 1 by 2 1 by 2. So again you will get 4 here, and then this B transpose, which is 0 minus 1 1 0 minus 1 1, and into B, which is 0 1 minus 1 minus 1 0 and 1. So if you do this multiplication, you will get K by 2 here. After the multiplication, this is what you get as your stiffness. This is 0, so 0, and this becomes 1, then this becomes 0, and the last one will become -1, and then when we go for this, it is 1 into 0, so this is 0, then this is 1, and then this is -1, the last one is -1, then no, you can, of course it has symmetry, so this is also -1, and this would be 2, so it's symmetry and everything. So this is what you have the coefficient matrix for the second element. Now let us go to assembly, and I want you to do the assembly. So assembly are these two elements. First let me just write the global structure. So overall we have got 4 nodes, so there would be 4 degrees of freedom, and now these degrees of freedom I am writing in terms of the global node number. So T1, T2, T3 and T4 is equal to, on the right side, this part is 0, you are going to have some contribution here. So as far as the first element is concerned, how do we assemble it? So say these are the global rows and columns. So this is 1 here, 2 here, 3 and 4, and this is 1, 2, these are global rows and columns, and 4. So the first element, if you look at, be as per this distribution, the node numbering scheme, first local node is corresponding to global node 1, and second is second, but the third is actually global 4. So if you look at the connectivity for the first element, so element number 1, the connectivity, if you look at local and global, so the local node 1 is equal to global node 1, local node 2 is same as global node 2, but local node 3 is actually global node number 4. So what it means is, at element level we have got 3 rows and 3 columns in the stiffness, the coefficient matrix, and the first row will go to the global first row, second row will go to the global second row, but the third row will go to the global fourth row, and same way the columns. So that is how you will have to assemble it. So now can you assemble it? So the what is the first element now, because I have to roll up and down. So the first element is, first row is 1, -1 and 0, and of course k by 2 is there, and that's there in both. So let me write here as k by 2, and this is 1, -1 and 0, right? So 1, -1, 0, where will the 0 go? It will go here. Then the second row is -1, 2, -1. So you have -1, 2, then -1 will go here. Then the third row is 0, -1, 1. So 1 is that, it will start here, 0, -1, and then 1 will go here. So this is the contribution of the first element coefficient matrix to the global system. Then coming to the second, for the second element, if you look at element 2, again local to global. So what we have is local 1, 2 and 3, local 1 is equal to global 1. That is how the connectivity, if you see here back, see for the second element, this is local node 1 corresponding to global 1, this is local node 2 which is corresponding to 4, and then 3 is corresponding to global 3. So this is 1, 4 and 2. So this is 4 and then this is 2. So what it means is, pardon? No, this is 3, I'm sorry, not 2, 3. So this is 3. So what it means is that the first row will go to the first row, but the second will go to the fourth, and the third will go to the third. So now let us take the first row of the second element. K by 2 is there, which I have written here outside, and then it is 1, 0, -1. So of course the first row goes to the first row, and but the column wise, so now if you look at here, this will be added here. So let me change the color. So here +1, and the second then is going to actually 4. So this 0 will be added actually here, you follow, and then the third is going to global third. So that is this -1 will be coming here. So this one goes here, this 0 goes there and this minus 1 comes here. That's the first row. Now for the second row, which is 0 1 minus 1, the second is actually going to the fourth row and then corresponding column. So first is actually 0, so you will be adding it here, then the second means, so which is 1 will be added here, and then the third is 2, which would be coming here. So is that right? No, which is we are taking the second one, so 0 1 minus 1 here, not 2, I'm sorry, looking at a different value. So this is minus 1. So this is the second row of the second element is going to fourth row, and column wise first, fourth and then third. So see, this is going to first column, this is going to fourth column, this is going to the third column when you look at these. Then the last row of that, 3 goes to 3 and the column is same manner, so this will be minus 1 here, and then this minus 1 will go actually here, and then this 2 will come here, and wherever there is no contribution means those terms are actually 0. So this is what you have finally as the assembled coefficient matrix for the global system. So I hope are there any doubts or questions on this? Yes, about the assembly, you should be clear about So yeah, as long as you understand this connectivity, that is local, it's a 3-noded element, so always you have to have 3 nodes, and they are corresponding to certain global node numbers. So once you define this, your rows and columns from local to global mapping is done through this. So for the first element, first row goes to first row, first column goes to first column, second row goes to second row, second column goes to second column, third row and columns go to fourth row and column. So same way here for the second element. So that is how we do the assembly. As far as there is no distributed heat flux, so these are going to remain 0. Now for the second one, what I am going to do is write the contribution of the what we evaluated here, this load vector, which is 0 to 2. So that I am going to add to as per the first element connectivity. So 0 will come here, 2 will come here, and then this will actually go there. Okay, and remaining portion, what you can actually see that as far as the contribution for the along this Qn is 0, along this Qn is 0, so there are no contribution. As far as this is concerned, from one positive another negative, so actually although they can contribute to global node 1 and 4, but they will cancel out. But from 1 and 3 also this edge, because the temperature is prescribed, so again there would be some unknown flux either entering into this or going out of this, but we don't know that. Ultimately that is going to contribute to node 1 and 3. So there would be some additional global node 1 and 3. So 1 means let me add some Q1 here, and 3 means let me add here some Q3. I am just saying these are unknowns. You follow this, why I added this? No, because with this edge, if you look at this edge, there would be some unknown flux, and even it may not be constant, it will actually function of y. But when we integrate this Q and ds along this edge, H transpose Q and ds along this edge, only the shape function corresponding to this node and shape function corresponding to this node are going to be non-zero along this edge when you are looking at the second element. The shape function corresponding to this node along this edge is going to be 0. So that means it will only finally that integral would be non-zero corresponding to 1 and 3. So that is what I have added, that let us say that integral is contributing to this Q1 and Q3, which are unknowns. You follow this? No. So not followed, right? So actually if you look at the second element, because there the temperature is prescribed, so there would be some heat flux either entering into the system or leaving out of the system, but that is an unknown. But it will have a contribution to the cyclic integral. So if you want to evaluate that cyclic integral along that edge, because that edge is finally y going from 0 to 2, and an unknown flux which is a function of say Q1 but function of y, and then you have of course H transpose into dy with a minus sign, of course what I had put. Since this is an unknown, but what we know is because this we are evaluating at x equal to 0, So only shape functions corresponding to the nodes on that edge, that is what I was saying, that the shape function for this element, the shape function 1 and 3 would be non-zero along this edge, but L2 would be 0. So that means when you look at this integral, this would be minus integral 0 to 2 qn, this is an unknown function of y. Here when you look at this term is going to be non-zero, L2 is 0, L3 is going to be non-zero, evaluated of course at x equal to 0 dy. So let us say that integral 0 to 2 q and y L1 dy is capital Q1 with a minus sign included in that, and integral 0 to 2 q and y into L3 dy minus is equal to q3. That is what I have added here. Okay. Now, so once we have assembled system, then next is the boundary conditions. So what are the boundary conditions? Boundary conditions are now, what we know is the temperature in terms of temperature. So you have actually if you look at the assembly, this T1 and T3, because now this entire edge is maintained at 100 degrees Celsius. So T1 must be 100, T3 should also be 100. If we use more number of elements, so whatever nodes are lying on this edge, all of them will have temperature equal to 100 degrees Celsius. So the boundary conditions are, one is that T1 in terms of global nodes is 100 and 1, 2, then that 3, right? So I numbered 3 and 4, yes. So T3 is also equal to 100. So see then, but we do not know the other things. If you look at, we don't know this, we don't know this. The other things we have taken care here. So now if you look at, we know that T1, we know T3. So what we can do is, because T1 and T3 are known, so corresponding to these we will have unknown flux, heat flux, total heat input at node 1 and 3. That is what is for maintaining a constant temperature. Some heat has to be taken out or taken inside the, depending on the problem. In this case it will be taken out at that particular point. So first what you can do now, since T1 and T3 they are known, first we can take equation 2 and 4, solve for T2 and T4, and then we can solve for Q1 and Q3. So based on these boundary condition, now you solve equations. This is 1 and 3, so 2 and 4 for T2 and T4, and then solve for Q1 and Q3, whatever I have written. Okay, so I think okay. So now if you want to take this equation 2, so that equation 2 is this is k by 2 of course outside there. So you have to write the equation 2 as k by 2. I am just taking only those two equations and then we'll put the values. So if you look at the second row, minus 1 to 0 minus 1, is that right? Yeah, minus 1 to 0 minus 1, minus 1 to 0 minus 1. Here the entire vector, so T1, T2, T3, T4 is equal to, this side you are taking only the second and fourth equation, so that is actually 2 and 2. That is what you will get in the second and third equation. Because T1 and T3 they are non-zero values, so I am accounting for that and you have to take that to the left hand side, no, right hand side. And the fourth equation, this coefficient is 0, minus 1 and 2. 0, minus 1 and 2. So these are second and fourth equations. Because T1 and T3 they are prescribed, and so there is a corresponding unknown kind of reaction flux Q1 and Q3. So first what we do is we take equation 2 and 4, solve for T2 and T4, and then go back to equation 1 and 3, you can get Q1 and Q3. This is similar to what we were doing earlier. So now since the T1 and T3 they are prescribed, their contribution you can take in this equation to the right hand side. So finally here you will have k by 2 and you will have 2 minus 1 and 2, and this side you will have T2 and T4, and the right side you will have of course this 2 and 2. In addition, you are going to have, no, in the first row you are going to have this minus 1 into 100, and then of course 0 into T3, so we will have minus 100k by 2, so minus 50, so this side we will have also plus 50k. Are you understanding? You just know, because T1 and T3 they are given as 100, so this element into T1 you are taking to the right hand side, and since this into 0, anyway this term is 0, so that does not contribute anything. When you look at this here, 0 into T1, that is of course 0, but this is minus T3, so minus T3 is again 100, so we will have that as again plus 50k. So this is your equation, K is your thermal conductivity. Now you can solve this for T2 and T4, these two equations, that solution you can do. Once you get T2 and T4, then you can work out that what would be Q1 and Q3. And of course you cannot still get exactly the, once you get the temperature fields, then you can, if you want to find out exactly how is the flux distribution along this boundary where the temperature is maintained, then you will have to take minus k into del T by outward normal is along minus x direction, so minus k del T by del minus x will give you exactly what would be the heat flux along this, because Q1 and Q3 will only give the lumped values of those at this node and at this point, that is node 3. So this is how the entire solution process will go about. And once you have done this, that's the solution of the problem. We can look at what are the temperature inside and the distribution variation along x and y. So this is how you solve problems. So you would see, obviously, two-dimensional problems are more involved, but they, once you understand the concepts, you can always write a code, say MATLAB or Fortran or C code, and you can do all of these. So you will have to give your input data, program does all these calculations and gives you the final result. So I think I'll stop here, and we will continue. So the next class, now what I'll do is, this is formulation in physical coordinate space. So we are done for a triangular element. Similarly, if you want, you can do a 6-noded triangular element in a similar manner, so that you can do as your actually home assignment, self-reading. And so the next I will discuss is formulation of rectangular elements in physical coordinate space, as an example of a 4-noded rectangular element, and then we will move on to formulation in natural coordinate space. So more time we are going to spend in the formulation based on natural coordinate space, because that is what is mostly used for almost all the 2D and 3D problems. Okay, so that will continue. So if you have any doubts or questions, you can ask outside.